Hello everyone, welcome to this webinar on configuring network policies with Project Calico and Google Kubernetes Engine. My name is Janakiram. I'm going to be the presenter for the day. But before I go any further, let me bring up a quick poll to make sure that you are able to follow this presentation. So I'm going to launch this poll to figure out your AV experience. So tell me what you see on the screen and what you hear is clear. Excellent. All right. So I'm very excited about this session because it's something very new and very important for running production workloads on Kubernetes. But if you are attending MI2 webinar for the first time, let me set the context. So MI2 stands for Machine Intelligence on Modern Infrastructure. Every alternate week, I bring one of these tracks where I cover Kubernetes, service mesh, network policies, Prometheus monitoring, and relevant technologies under the infrastructure track. And I cover IoT, AI, machine learning, and edge computing under the intelligence track. This is a completely independent and neutral platform to explore emerging technologies. I am not biased. I am not trying to market or sell any specific platform or a product. This is just a forum, a platform to share what I'm learning in the emerging technology space. So my name is Janakiram. I'm a Google developer expert, certified Kubernetes administrator, and certified Kubernetes app developer. Very passionate about sharing my understanding and observations with the community. So let's get started. I'm going to kick off this session with a quick introduction to network policies in Kubernetes. This is basically talking about how network is structured within a Kubernetes cluster and what are the limitations with the default environment and why we need to use network policies. Then I'm going to introduce a quick overview of Project Calico, which is an open source project meant to bring zero trust security to Kubernetes and even virtual machines and even bare metal servers. Then we'll take a closer look at network policy, and I have a few demos that are pretty interesting and they'll drive the point across. So to gauge your experience and to structure this session better, I want to ask you a couple of questions. So let me bring this up. So how do you rate your Kubernetes skills? Are you an expert, an intermediary user, a beginner, or an absolute novice? All right. Most of you are intermediate users. That's actually good because I assume you understand how pod services and the communication within Kubernetes works. So that would really help you appreciate the capabilities of Project Calico. So that's excellent. I'm also curious to find how many of you run Kubernetes in production. So let me know if any one of you is running Kubernetes and workloads in production. So interestingly, 50% of the audience are actually running Kubernetes in production, which is excellent. All right, so that does give me a good sense of where you are in your journey and how to structure this content according to your experience and your expertise. All right, so let's get started, and I want to walk you through the basics of Kubernetes networking. It's a quick recap. Those of you who are not very familiar with Kubernetes networking will find this useful, and even otherwise, if you're familiar, this is going to be a quick refresher. So Kubernetes uses a flat network that eliminates the use of NAT. Whether a node is talking to another node, a pod is talking to another pod, or a node is talking to a pod, or vice versa, we have a flat network that is completely transparent. You don't need to use NAT. You don't need to use any workarounds to enable communication between entities of Kubernetes. And this is one of the biggest advantages of using Kubernetes. It's extremely transparent and it has its own network that is managed by the cluster. and it is completely flat. So it doesn't use any complex schemes or protocols or topologies for enabling communication across various entities. A fundamental concept: containers within the same pod share common namespace. That is, within a pod, if you're running two containers, they see each other on the local host namespace. So if you have an Nginx pod listening on port 80 and you have a logging engine or an agent like FluentD, and both of them are running inside the same pod, the logging agent can actually talk to Nginx using localhost. So they share the same namespace. And this avoids, again, a lot of complicated schemes to make sure that containers are able to talk to each other in the most transparent form. Similarly, a pod can talk to another pod using the IP address, but pods are ephemeral. They can get terminated at any point. There is no guarantee that this pod is going to run forever and it's going to retain the same IP address. So hardwiring a pod's IP address in communication is not a good idea. So to provide some kind of an indirection, we use a service, and service could be of cluster IP, node port, or load balancer. And this acts as a proxy to communicate with the pod. A collection of pods that fall under a specific criterion, like matching a set of label selectors or using annotations, the service proxy will route the traffic to one of the pods that matches the criteria. And this is, again, a very powerful concept. You can start with one pod and later on use the deployment or a replication controller to scale the pods. And as long as the pods follow the same metadata, that is labels and annotations, they actually participate in the traffic and the inbound request. So the service acts as a kind of a load balancer that routes the traffic to one of the pods matching the condition. kubedns or CoreDNS provide the name resolution. So basically, there is an FQDN, a fully qualified domain name associated with the service. It depends on the namespace that it runs in, and it's a well-defined, well-known endpoint. And the service can be easily resolved by its FQDN. And that resolution is provided by kubedns or CoreDNS. There are other third-party solutions as well that you could actually integrate with Kubernetes to enable name resolution. But this capability will enable pods to basically use a well-known endpoint to talk to another pod, because as I mentioned, pod IP address is completely ephemeral, but a service FQDN is permanent. So you always talk to the service FQDN, and that name resolution is provided by kubedns. By default, any pod can communicate with any other pod as long as there is a service that is associated with it. Or even if you don't have a service, you can still talk to the IP address, but there is no guarantee that it will be retained. But technically, there is no restriction on a pod communicating with other pod. So in short, in summary, there is no concept of a firewall in default Kubernetes environment. So when you set up default Kubernetes using kubeadm and using Flannel as your overlay network, there is no firewall. So there is a load balancer, which is coming close through the service and the proxy. But if you want to really block certain ports or allow traffic to a specific port, or have security group like capabilities within Kubernetes that is not provided by Flannel, which is the default network mostly used in Kubernetes environments. So that is one of the limitations of Project Flannel, Flannel overlay network, and also the default Kubernetes environment. Now that's where we have many other alternatives to Flannel, and Project Calico is one of those. So Project Calico is basically an optional plugin for Kubernetes. It's an open source networking project that can be integrated with containers, VMs, and orchestration engines. So Project Calico is not just meant for Kubernetes or containers. It can be even integrated with VMs and even bare metal servers. So it has nothing to do with the host environment. It could run in Kubernetes, in EC2, in data center, in a bare metal physical environment, or even in plain vanilla Docker containers outside of Kubernetes. So it's an open source networking project that brings in many capabilities to a variety of hosts. It basically delivers interoperability between VMs and containers. So if you have legacy workloads and modern workloads operating in the same environment and you want to define interoperability, Project Calico is a very mature project to basically uh, route the traffic and enable interoperability between VMs and containers. It provides rich network policy model for workloads. It brings firewall capability to deployments. And this is one of the core capabilities. And if you implement Project Calico, you can actually go for close to open. So basically in the security context, there are two schemes and it's almost binary. Either you have open to be closed or close to be open. So open to be closed is the default environment provided by Flannel, where any pod can talk to any other pod in any namespace. The moment you integrate Project Calico, you can basically go for deny all, which is close to be open. So you will block the traffic to all the pods and you will explicitly open the traffic between one pod and the other. And that is bringing in the zero trust security, where you don't trust anything and unless you explicitly enable communication between two entities. It also integrates well with Istio and Envoy. So integration with Service Mesh is one of the most recent additions to Project Calico. And it is exploiting Linux kernel's forwarding and access control features. So it is well integrated with the lowest level of the operating system capabilities. So there is no overhead if you're using Project Calico because it technically integrates very well with core Linux kernel capabilities. Of course, it's tightly integrated with Kubernetes. Uh, After you set up the kubeadm and define your CIDR for the nodes, you can basically apply a YAML file, which is calico.yaml, and it is the only thing that you need to do. After that, Project Calico gets deployed in your Kubernetes cluster, and you can start using it as the default network. It's available in mainstream cloud-based Kubernetes environments, that is managed Kubernetes environments like Google Kubernetes Engine, Azure Kubernetes Service, Amazon Elastic Kubernetes Service, IBM IKS, OpenShift, and so on. This demo on this session is based on Google Kubernetes Engine because it's one of the easiest environment to get started with Project Calico. So now that we understand the core capabilities of Calico, let's take a closer look at the network policies and how we can bring in firewall-like features to our Kubernetes deployments. So the first important thing to understand is if there is a pod, the pod can basically have ingress, that is inbound traffic. And the pod can make outbound calls to another pod or to the internet, and that is egress. Now, if you're familiar with EC2, VPC, virtual networking in any cloud environment, including GCP or Azure, you know that you can actually define firewall rules for both ingress and egress. So you can basically define what ports are allowed on a specific VM or on a virtual network. And you can also define the outbound traffic conditions like whether the VM can make an outbound call to the internet or it can talk to one of the other subnets within the virtual network. So you can define very, very fine-grained rules for VMs and virtual networks. And that entire topology and the way we deal with it has reached a good maturity level. And today, most of the production workloads take advantage of those security groups and firewall rules for securing the deployments. Now, one of the biggest advantages of using Calico is bringing those capabilities to pods. So if there is a pod running, it may be invoked or it may be used by another pod. So there is an ingress, which is inbound connection, and the pod can talk to another pod within the same cluster, or it can make an outbound call to the internet. That's going to be egress. Now, ideally, what we want to do is to create a set of rules so that we have fine-grained control on inbound traffic and also outbound traffic. So like a typical firewall, you can actually define a set of rules. For example, when the inbound ingress rule is defined, you can actually restrict the traffic to a specific port. For example, on port 80 or 443, where you're actually exposing your web front end and you want to block everything else. So you can actually define what ports are allowed as a part of the rule. You can also define an IP block. And an IP block is a traditional CIDR scheme. This is very similar to the way you define an EC2 security group or a VPC security group. So you'll define the CIDR based on the octet, and it is going to restrict the traffic only to that specific CIDR, the IP block. Then you can also define a namespace, and it actually becomes pretty interesting from now, because if you have pods that are deployed in different namespaces and you want to selectively allow traffic originated from a specific namespace, you can actually define that. And similarly, you can also define which pod is allowed to talk to this by defining some criteria based on the labels and annotations. This is not the most comprehensive set of rules, but these are the most commonly used ones. Similarly, when it comes to egress, you can actually define what is the outbound port that is allowed from this pod, and what is the IP block. So basically it cannot talk to anything other than the defined port and the defined IP block. For example, if you have a web server and you want the web server to talk to MySQL pod, so you'll actually define the pod, the port on which the MySQL pod is listening, and the IP address that is associated with the service exposing the MySQL pod. So you'll actually define that as an IP block. And then this pod cannot make any outbound call except to that pod on that specific port. So that is the egress policy that you define, rule that you define. So once you have a set of rules defined for ingress and egress, you actually wrap it in a policy. So basically, in the context of Project Calico, a policy is a set of rules either affecting ingress or egress or both. So once you define a policy for ingress or egress, then there are a set of rules, and these rules allow or deny traffic. So if you understand how firewalls work in a typical IaaS environment like GCE, Amazon EC2, and Azure VMs, you can relate to those concepts because it's very similar. Now, let's actually understand this better. So I'm going to show you a typical YAML file that exposes or that defines a Calico network policy. You can actually take this and apply to any Kubernetes cluster, but if there is no Calico environment configured, Kubernetes will simply ignore it. But assuming you have a cluster fully configured with Calico network and a CNI plugin, you can actually take this and apply it to your cluster, and then all the rules get affected, all the rules get deployed or becomes enforced. So this is the YAML file, and let's understand some of the key building blocks of this. First thing, this network policy is applied to any pod that matches the role DB. So it all starts with the pod selector. Because the network policy could become universal, you want to apply a filter right at the beginning under the spec section so that it is applied to only those pods that match a specific condition. And in this case, we are now isolating pods that match role DB. For example, this could be a MySQL pod. So in the default namespace, that is what is defined here. And then we are also defining the pod selector that says any pod that matches the label role is equal to DB. So that is the first section. And this becomes very important because this will define which pods are going to be isolated and will participate in this policy. Then the second is the policy type. And here we are defining both ingress and egress policy. So that is the next section or the building block of a network policy. You can actually have just ingress or egress or both. And in this case, we have policy types defined for both. And since we defined the policy type for ingress and egress, we need to go ahead and define the rules for those. So it all starts with the rule for the ingress. So here there are a bunch of things. So first thing, this pod can accept traffic only from other pods that fall under this range, that is defined with the CIDR. So because we are actually defining /16, it is covering everything from 172.17.0.0 to 172.17.2.255.255. It's like a pretty broad range. Now, we want to restrict to a specific CIDR, then we can actually say except anything that matches this octet. Now, even though we are covering a pretty broad range here, we can narrow it down with an except clause. So block any request that is originated from an IP address in the range of this. Basically this is 0 to 2, but if the origin is carrying an IP address of 1.0 to 1.255, block it. That's what is defined here. So that is about the IP block. And this will basically allow or deny traffic based on the CIDR of the origin. Then we are actually defining the namespace selector, and we are not explicitly defining a namespace. So here match labels will basically say that any namespace that has the label project is equal to my project, we can allow the traffic. So this is the second level of filter or the rule that we are applying. So the origin should be inside a namespace which has a label called project is my project. And then we also have another rule which says pod selector, and that should match the role front end. Only when all these conditions are met, the traffic is allowed. And finally, it cannot target any other port other than 6379 because it's a database. So just with a few lines, we enforced quite a powerful policy. First, we defined the IP address range, then we defined the namespace, and this could be like a very good mechanism to basically isolate or to draw partitions in the same cluster running multi-tenant or very different set of applications. For example, a web server running in finance department cannot talk to a database in HR because the namespaces are different. So you can also have a dev and production namespace, and the dev front end cannot talk to a production DB. So you can actually impose those level of rules by using the namespace selector. And then the highest level of trust comes in when you actually have the pod selector, because this is where the annotations and labels come into the picture. And finally, of course, the port. Then we have egress, and egress in this scenario is basically to allow connections from any pod in the default namespace with the label role is equal to DB to the allowed CIDR on port 5978. That means this pod can only make an outbound connection to one of the IP addresses that fall in this range and the port matching 5978. So this is a very comprehensive network policy. And if you notice, this is super critical for production workloads. So if you carefully define network policies for each of your pods or each of your microservices, you are in total control, because you are actually denying traffic, um, any traffic, other than the legitimate sources or legitimate callers will be completely dropped or denied. So that is a zero trust security, where everything is by default closed, and you explicitly open what kind of traffic and what kind of a rule is going to allow the traffic. So that is about the theory about a network policy and Project Calico. So the bottom line, Project Calico brings in firewall level capabilities to our applications. And now I don't want to spend any more time on slides. I'm going to jump into a demo. And I have 3 demos. First, we'll explore the Calico environment on Google Kubernetes Engine. The second one is the out-of-the-box sample that the folks working on Project Calico has published. It's a fantastic sample, and we are going to use that to understand the core concepts. And then I'll show you a real-world deployment where we have a WordPress application running on MariaDB and PHP application, and where we are actually going to allow and deny traffic, and we'll see that in action. So let's get started with the demo. Now, I'm using Google Kubernetes Engine, and the reason why I really like this is one of the most mature managed Kubernetes offerings in the industry, in the market that's available. Not only that, with just one checkbox, you can deploy Project Calico in GKE. So this single checkbox, enable network policy, is going to basically replace the default overlay network, which is Flannel, with Project Calico. And a special mention about Tigera, which is the owner of Project Calico, and they also have a commercial offering, and they basically maintain Project Calico along with other contributors. So Google has partnered with Tigera to bring Calico into GKE. If you are using command line, you can actually see that this key or this switch, enable network policy, basically uses Project Calico instead of the default Flannel network. So I have gone ahead and launched a default cluster modified just for the network policy. And here we are. This is my 3-node Kubernetes cluster running in Asia South 1A, Mumbai. And this is currently enabled for network policies. So network policy is enabled. And that's all. That is about the browser and the GKE environment. Other than this, it's a normal Kubernetes environment. So nothing specific about it. So let's get started with the first demo, which is basically exploring the Project Calico environment. So this is not the most comprehensive discussion on Project Calico. I plan to do that in one of my upcoming sessions, but the focus for this session and this demo is to show you the capabilities, not the installation of Calico or the internals of Calico, but it actually helps to understand how this is integrated with Kubernetes and how do you verify the installation. So first thing, this is actually installed as a daemon set. So if you actually look at the daemon sets that are currently deployed in the GKE environment, you notice that there is a daemon set called Calico node. And because we are running a 3-node cluster, obviously there are 3 pods that are associated with this daemon set. We can go ahead and try this command where we are applying a label. So get pods label is Calico node, and we actually retrieve all the 3 pods that are a part of the daemon set. So every node in GKE is basically running Calico, and that is talking to the CNI plugin. So that's how we have the network configured. If you're not using Kubernetes, for example, you're using other orchestrator or even VMs or plain vanilla Docker containers, you can still use Calico. So you need to configure certain environment variables. In our case, we're actually using Kubernetes, so we'll point the data store type to Kubernetes. And the significance of this is basically we are telling Calico CLI where to look for the HD database, because like most of the other Kubernetes-based plugins and Kubernetes-based workloads, Calico relies heavily on HD for maintaining the state of the network. So we need to tell where the HD database is. So by setting up this variable, data store type is Kubernetes, we are actually telling Calico CLI to look for the HD endpoint within the kube config. So the next thing that we're going to do is to export kube config so that Calico Cuttle, the CLI, can actually get access to the environment. So those two environment variables essentially configured Calico Cuttle. So now when we actually run Calico Cuttle get nodes, we see the nodes that is responsible for running Calico. So the same thing is also visible with kubectl get nodes. So essentially they are the same. But remember, Calico Cuttle is independent of Kubernetes. So if you're running a bunch of VMs and you set appropriate environment variables or pass those parameters to the CLI, you can actually retrieve even the VMs. You can also get the profile. So get profile will show you all the CRDs. So CRDs are basically the resource definitions that are installed within Kubernetes. So basically, this is deployed as a set of CRDs and custom controllers, and it extends Kubernetes functionality to provide additional network capabilities. So get profile will show you all the Calico specific components that are installed within Kubernetes. So this first step is just to get familiar with Calico and to emphasize on the fact that you can use Calico Cuttle as a standalone CLI. But if your Calico network is running within Kubernetes, then you got to set those environment variables so that the CLI can figure out where to look for the HD database and how to retrieve the configuration. And this is a good starting point to basically verify the installation of Project Calico within the environment. So now that we are done with that, let's go ahead and deal with a slightly better application, meaningful application that represents some real world use case. So again, this is a fantastic sample that is available on Calico's documentation. So what we're going to do here is to basically deploy a very nice application. It doesn't do anything fancy, but it provides a great user interface for us to visualize how the network policies are being imposed. So we're going to deploy a bunch of manifests that results in the creation of namespaces, creation of some pods, some services, and so on. So let's go ahead and deploy each of those. So first thing, we are going to deploy the, let me move to the right directory. So stars. So here we will actually deploy the namespace. So now when we actually run this, what happens is we end up getting a new namespace, and that namespace is called stars. So you can actually verify that here. So the first YAML file does nothing but creating a new namespace called stars. Then we go ahead and create the second artifact through management UI.yaml, and let's explore what's inside that. So management UI again starts by creating a namespace, and then it creates a node port on 9001, and then pointing to 9001, and then it deploys a replication controller that runs the UI to visualize the deployment. So a replication controller, a node port service, and a namespace. That's what happened when we ran the management UI.yaml. Then we're going to, okay, let's verify this. So kubectl get ns, we now have management UI, right? along with stars that was created earlier. Now we are going to, let's actually run backend.yaml, and this is going to result in creation of a new replication controller called backend and a service called backend under stars namespace. So backend, this is going to be created in stars. It's exposed on 6379 and a replication controller that is based on this image. After we deployed the backend, we'll go ahead and deploy the front end. Again, in the same namespace, it is inside the stars namespace, and we have a new microservice called front end running inside the same namespace as the backend. So we have a three-tier architecture. There is a backend, there is a front end, and now we are going to deploy the client. So client goes in its own namespace. So this is going to result in three things. It's going to create a namespace, it creates a replication controller, and it exposes the client through a service. So you can also look at the YAML file. So a namespace for client, and then a service. And of course, this is based on one of the images provided by Calico's team. So excellent. So now we are done deploying this. So let's quickly look at some of the essential building blocks of this demo. So getNS will show us that this demo has three new namespaces: stars, client, management UI. And when you run kubectl get all under stars, you'll notice that it runs the backend and front end. It runs the service. And of course, they are packaged and deployed as a replication controller. So you'll see that artifact as well. Similarly, when you look at the client namespace, you notice that it's just running one pod under the replication controller called client, and it is exposing a service with cluster IP definition. Similarly, there is a namespace called management UI, and this has one pod deployed as a replication controller with count 1 and a service management UI. The most interesting part is the service management UI because it gives us a visual representation of the deployment. So what we'll do is we'll actually go ahead and set up a kubectl port forward so that we can access it from the local host. So we are now tunneling into port 9001 exposed by one of the pods, one of the services. So this is now available. So what we can actually do is open the browser with 9001. There we go. This is a beautiful application which helps us understand how Calico works. So now what this actually tells us is there is a front end, there is a back end, and there is a client. And this is a three-tier architecture that has been migrated to microservices. So ideally, the client should talk to the front end and front end should talk to the back end. But in this case, as you can see with these white dots moving around, any pod is able to talk to any other pod. The client is talking to the backend, which is not the right way. The front end is talking to the client. The front end is also talking to the backend, and basically no restrictions. Every pod is talking to every other pod. So what we're going to do now is to bring in some policies, and as we start applying them, we should be able to visualize using this console. A quick disclaimer, I had some issues, particularly the UI acting a bit funny. So I hope it's not going to be the case, but in case we see that, I will have to repeat the demo. So bear with me. All right. So now we are able to visualize the interface. So what we'll do is we will deploy a new policy called default deny. So default deny is interestingly blocking everything. So when you look at default deny, it says pod selector, match labels, empty braces. What this basically represents is all the pods, and it doesn't even define which namespace. So if you deploy this in any namespace, by default, all the pods will get blocked. That is the default deny. So we run default deny in stars namespace. That means suddenly the client cannot talk to the front end or the back end. Not only that, we're also applying default deny to the client namespace, which means even the client gets blocked. So the outcome of this step will be basically a blank browser. We shouldn't be able to see anything. So that is what is going to happen when we run these two commands. So let's go ahead and run this. First, we are blocking the traffic to all the pods running inside the stars namespace, which is essentially the front end and the back end. And then we are going to, okay, now at this point, if you actually run this, so only the client is jumping around. And this is the funny thing that I was mentioning about. Okay, so now we are going to even apply the deny policy to the client namespace. So at this point, when we come back and do a refresh, okay, so we don't even see the client because the client is blocked. It cannot receive the traffic. The front end and back end are blocked, so they cannot receive the traffic. So the UI is blank. Not surprising. Now, if you actually look at the next step, what we'll do is we will selectively enable the traffic, from UI to the front end and back end, and also selectively enable the UI to the client. So first, let's take a look at the YAML file that says LOUI. So LOUI simply says, inside the stars namespace, apply to all the pods only if the inbound request is coming from management UI. So basically here we're actually saying that the namespace should be having a role called management UI. So that is the policy that we are applying. And similarly, LOUI client, same thing, but applied to the client namespace. So that's the reason why we're actually running different namespaces. Now let's go ahead and run those two commands. So first we'll allow the UI to the stars backend, that is front end and backend, stars namespace, and then we'll also allow the traffic to hit the client. So now we should come back and do a refresh, and we are actually able to access the UI. But if you notice, the traffic between the front end and back end, the client and front end is blocked. They're not able to talk to each other. That's because we have only enabled management UI's access to the client and the stars namespace, but we haven't enabled the traffic between the front end and back end, the client and the front end. That's what we're going to do now. So now we'll actually open up the traffic to backend. So this is the policy that says namespace stars, pod selector. This is going to be applied to any pod that matches the role backend. And then only if the origin, the request is originated from a pod whose label matches role frontend, and if it is targeting port 6379. And if you go back and look at the front-end definition, so we have the role as front-end, and it is expecting the traffic to 6379. It is making an outbound call to that. So that's what is basically defined here. So similarly, when we have a front-end policy, so here it says namespace is stars, front end is the applied pod. We are isolating this and allow the traffic only from the client. Remember, it's a three-tier architecture. There is a client, there is a front end, there is a back end. So now we are allowing the traffic to flow in from the client to the front end to port 80. And that is what is defined here. Port 80 is the service that is exposed for the front end, and the back end is exposed using 6379. And that's how the policy is defined. So this is a front end policy that will enable the traffic to flow from the client to the front end. And this is the backend policy that allows the traffic to flow from front end to back end on appropriate ports. Perfect. So let's go ahead and apply those two policies. So backend and front end policy. So first we'll apply the backend, right? So once we run this, now what will happen is the front end will be able to start talking to the back end. So now there we go. So now the front end is actually able to make an outbound call to the back end. And this is the expected functionality. Now, the client is still not able to talk to the front end because we have by default blocked all the traffic with a deny all policy. Now let's go ahead and run that final YAML file that opens up the communication between the client and the front end. So let's run this. So now we have opened up the traffic between the client and the front end. And when we refresh the UI, there we go. So now, yep, that's it. Okay. So now this is exactly how it is supposed to be. Client talks to the front end talks to the back end, but the client can never talk to the back end. And this is the expected behavior and the ideal deployment topology for our microservices. Now you can take the same definition and apply it to your workloads running in the production. Nothing changes. That's the beauty of Project Calico. So this is the first demo that I wanted to show you. And the idea was to basically introduce the concept of, deny all, where you don't mention a namespace, you don't define which pods are being isolated. You start with default deny, everything gets blocked, and then you start explicitly allowing one after the other. So that was the first demo. Now let's actually go ahead and do something more meaningful. So we'll deploy WordPress, and we will carefully observe the behavior by applying the policies to both the front end, that is WordPress, and the back end, which is MariaDB. So let me switch to the WordPress directory and split the terminal window because we want to keep certain pods in a watch mode. Okay, so there are a few things that you need to do. I have already gone ahead and deployed Helm, but if you are not familiar with Helm, particularly when you're running Helm in GKE environment, you need to create some cluster role binding. So this is very important. And then you also need to patch the deployment to make sure that Tiller has appropriate access and has appropriate ports open. So you can actually read about the best practices of running Helm within GKE, but I have done all that. Now what we're going to do is to deploy a WordPress chart using Helm. So currently Helm is up and running. So when we type Helm version, it shows that it is running on both the client and server, which is excellent. Now we'll go ahead and deploy WordPress. So this is going to result in the creation of a few things. First of all, it's going to deploy a stateful set. So let's put this in watch mode. kubectl get pods. So you see that there is a stateful set. MariaDB is running as a stateful set, but with only one instance. Then there is the WordPress, which is actually running as a deployment, and that is running as a stateless pod. So in sometime soon, we'll actually notice both of them in running state, and we can also access the front end. So when you do kubectl get service, the load balancer is still not provisioned. It's going to take a minute. I could have actually run this beforehand, but I wanted to show you a live demo of deploying this end to end. So in a minute or two, we should see the pods both in a running state, one of one, and then the load balancer. There we go. So now the load balancer is also available. Let's copy this, but I'm also waiting for the pods to become available. So let's make sure that everything is in good shape. So kubectl describe pod. Okay, so MySQL admin localhost failed. Okay, looks like there is some problem and the health checks fail. This is a common thing with the WordPress Helm chart. It's going to take a couple of minutes for everything to become uh, available and move into the running mode. Let's see if okay, I think my last network policy hasn't been deleted. Looks like there is some problem with, yes. So, okay, so I think okay. So there is a default deny that's basically blocking my um, current pod. So no wonder it's not running. So let me refresh this. So I'm going to delete the network policy. Okay, so that is gone. Then I'll also delete this network policy that says default deny. Okay, and to be clear, so let's actually go ahead and delete this chart, which is np test. So I'm going to do a fresh deploy of the Helm chart. So we are getting rid of this. There was actually a deny all policy that prevented my pods from becoming available. The health checks constantly failed. So let's actually wait for this to get terminated and we will go ahead and deploy WordPress Helm chart all over again. Okay, so this is a live demo. This is not a recorded version. This is not a staged demo. So these things will happen. And it's an indication that this is actually a live demo. So bear with me as I refresh this environment by deleting all the previous network policies and terminating the deployment. It should just take another, there we go. So now I will go ahead and deploy WordPress all over again. Okay, so now this should quickly become available because the images are already pulled and hopefully they are available. So it should quickly move into running state. Okay, I'm waiting for two things to happen. One is the availability of both the pods. Both of them should be in a ready state. And I'm also waiting for the load balancer to become available so that we can actually access the WordPress front end from this through this Helm chart. So let's wait for just a minute. Maybe I should have deployed the Helm chart beforehand to save some time, but that's fine. Let's give it a few more seconds and it should be up and running. Okay, so the load balancer is now available, but we can't still access the pods because they are not in the running mode. Okay, I'm debugging this. So, okay, this is not a problem, but all right. WordPress seems to be running fine. Okay, I'm just going to wait for another few seconds. If this doesn't work, I will explain what I intended to do. But technically, this should just work. I know where we are going wrong. So we had default deny that was actually deployed, and it is universal. It is basically affecting my entire Kubernetes cluster. So I need to get rid of that. So what we'll do is, okay, so one more time, okay, kubectl delete namespace stars, okay, and we will get rid of all the namespaces that were created in the previous demo, because there is a universal deny all that is still enforcing the deny all, and that's the reason why we're actually experiencing this. Okay, I'm not surprised. So give me a second while I fix that. So basically I need to get rid of the previous demo to get rid of all the entities, and also delete the default deny all. And then magically you will actually notice that the MariaDB and the WordPress pods coming up. So this is the okay. So now what I'm going to do is kubectl delete this. Okay, so this is already deleted. So the reason why this is happening is we actually have a policy that is preventing the health check from running. So the health check will basically make sure that WordPress is able to send a HTTP 200 OK on port 80, and that is not happening because it's not able to talk to MariaDB. So there is some policy that is preventing from WordPress talking to MariaDB, and I'm trying to figure out what that policy is. And it actually looks like there is no network policy currently applied, but still something is preventing. So let's get rid of these entities. Okay, one final time, I'm going to basically get rid of my Helm chart and deploy it again. Something is definitely not right. This shouldn't be the case at all. Okay, so this is a plain vanilla cluster. We don't have anything on this running at this point. So okay, one final time. Hopefully it should come up this time. Otherwise, I'm going to wrap up this session. You get an idea. My apologies that this demo is not working the way it's planned. My cluster is currently messed up a little bit. I should have kept two different clusters. Looks like there is some network policy that's preventing me from running these containers, these pods. Nope. All right. My apologies. I'm glad at least the previous demo worked the way I wanted it to. So ideally, had this been deployed the way it was supposed to be, what I wanted to show you was the moment we go live, I would apply a default deny and immediately the health check would fail because WordPress will not be able to send HTTP OK, and it starts sending an error, and there will be a crash loop back. So there will be an exponential back off for the WordPress pod, and currently that is what is happening, because currently there is some policy that is preventing from the health check being run. And after that, I go ahead and selectively allow the traffic from the front end to the MariaDB database, and that would magically bring the WordPress pod into running state. That was the demo that I wanted to show you, but never mind. You get an idea. Basically, it's an extension of what we have seen in the previous demo, but more real world, more realistic, with a database and a PHP frontend based on WordPress. But that's okay. Live demos, this happens. It's not very often that I run into these issues in my live demos, but it's a lesson. I need to have 2 different clusters or do a proper refresh before I go ahead and run multiple network policies. All right, so let me bring you back to the slide deck. I want to thank our sponsors, Google Cloud, for helping me with the credits and all the technical expertise and validation of this content. Newstack, our media partner. All the presentations and the topics that I cover in MI2 will get published at the Newstack. So tomorrow by this time, you should be able to see a tutorial of everything that we have discussed in this session, published at the Newstack as a tutorial. So every MI2 session translates to a tutorial at the Newstack. Foghorn, a Bay Area-based multi-cloud edge company. Portworx, a container native storage company, again in Bay Area. I want to thank them for supporting me and sponsoring this webinar series. I'm very excited about announcing the next webinar, which is in the intelligence track. That's all about accelerating AI at the edge with Intel OpenVINO Toolkit. I'm going to show you how to accelerate inferencing of computer vision models based on Movidius and Mirai chips with OpenVINO toolkits. It's an interesting demo where we use OpenCV and OpenVINO toolkit to basically create convolutional neural networks and accelerate the performance. So again, sign up for that at mi2.live. This is going to be on Thursday, October 10th, 9 a.m. PT, 9:30 p.m. India time. All right, so finally, I want to bring up a quick poll. Sorry about the demo, but I hope you still found the content relevant. All right, thank you so much for that. 100% of you mentioned it's very relevant. Finally, how do you rate the quality of this webinar? I put a lot of effort in bringing you high quality content. It's very rare that my demos don't work, but most of the time I do a lot of dry runs and I make sure you get a better experience. But all right, so thank you. Most of you felt this has been very good and also excellent. It's very encouraging. I'm committed to bring you high quality content and cutting edge technologies. So in the next quarter, which is October, November, December, I'm planning to bring you more content around Prometheus, Service Mesh, and more on modern infrastructure. And at the same time, I'm going to cover more of edge computing and AI at edge as a part of my intelligence track. So thanks again. I will see you in the next webinar.